Hello everyone, this is the second video in the tensor analysis lecture series. Okay, we did yesterday the brief introduction into tensors. We studied covariant tensor, contravariant tensor, tensor of rank 2, tensor of rank 1, 0, 2. So today we will continue that. Okay, and so today we will continue. We left at metric tensor, so today we will continue the metric tensor. Okay, the metric tensor. So metric tensor is actually how is it defined? Like ds square, the distance square can be defined as we know dx naught square minus dx1 square minus dx2 square minus dx3 square. Right. So this is your ds square. So this can be written as also ds square is equal to g of alpha beta, g alpha beta, g covariant alpha beta, g dx alpha and dx beta. Okay, so this g alpha beta is actually your what? Hmm? This is a what covariant tensor of rank 2, right? This is rank 2 covariant tensor and known as the this is known as the metric. This is known as the metric tensor, right? This is known as the metric tensor. Okay. Sometimes it's also called simply the metric. Right? Okay. So G alpha beta can be a function of coordinates, not necessarily diagonal. It can be okay. There could be cross terms in G ds square like ds dx1 dx2. These terms can also arise in this dx so G alpha beta or sorry d square dx2 dx3. Okay, then dx naught dx1 these terms can also arise. They are not completely diagonal elements. Okay, diagonal elements means simply 1 1 0 0 1 1 2 2 all that. No, these can also arise in ds square. Okay, yeah. So the metric g alpha beta transforms as a covariant tensor of rank 2 and can be verified at once. Like let's say suppose um, in one reference frame sigma. Suppose we write the transformation. Suppose I write d s dash square is equal to g mu nu dash, okay, dx dash mu dx dash nu. All right. Suppose this is the um, ds dash square. So if we transform it, okay, since we know ds square ds dash square is equal to ds square. Okay. So the transformation under the transformation what? Under the transformation x alpha, x dash alpha. This is the transformation. So we have right now I can write g dash mu nu this one g dash mu nu dx dash mu dx dash nu, okay, is equal to g alpha beta dx alpha dx beta. Yeah, all right. So from here I can write g dash as I'll take this to this side. G dash mu nu is equal to g alpha beta. This is dx alpha by dx dash mu dx beta by dx dash nu. Alright? Yeah. Or we can simply make them partial derivative. Okay. If I do this del x alpha by del x dash mu or del x beta by del x dash mu. Right? Yeah. And g alpha beta. So this can be written also. Okay. From here we do that. So let's write some properties. Let's see the properties of the metric tensor. This is the metric tensor. Okay. So properties of the metric tensor. Properties of the metric tensor. So first property is it is symmetric under the interchange of indices. Okay, symmetric under the interchange of symmetric under the interchange of indices or indices whatever. So if I write it like we can write it like G alpha beta should be equal to G beta alpha, right? Yeah, this is for all alpha beta. Okay? This is the sign for all. Okay, so next is its contractive product. Next property right now, its contracted product. Its contracted product with the metric tensor. Its contracted product with the metric tensor in covariant form. Sorry, in contravariant form. In contravariant form gives the Kronecker delta. Okay, gives the Kronecker delta, which can be shown to transform, which can be shown to transform as a metric, as a mixed tensor, as a mixed tensor of rank 2. Yeah. Okay. So I can write it like G mu alpha covariant G mu alpha contravariant G mu beta. We can write it as G delta alpha beta. Okay. So this will result in a Kronecker delta, not G alpha beta. It will be delta alpha beta. Okay. So delta alpha beta will be 1 when we know it, like when alpha is equal to beta, it is 0 when alpha not equals to beta. Right? Suppose we know. Um, okay. So next the symmetry property actually ensures that there are at most like 10 independent components of G alphabet. Okay, in a 3 plus 1 dimensional space time. So one can compose, like suppose I can write ds square is equal to g00. This one I told you yesterday, but let's do it again. G0 dx square and 2g 0 1 0 I dx0 dxi. Okay, and then gij dxi dxj, right? So this is can be the expression. So one term for mu is equal to 0. This is only one term. Okay, this is actually what this one is actually what sum of three terms. Okay, sum of three terms for what mu is equal to 0 and this mu is equal to I. Okay, and the factor of 2 is for symmetry, and this one is what sum of six terms. This is sum of six terms and sum of six terms. You will slowly understand, don't worry. So mu is equal to I and mu is equal to j. Okay. Yeah. Due to symmetry, what? Due to symmetry, gij is equal to gji. Right. So yeah. Okay. So the norm of the vector will be what? Norm of the metric tensor will be that a norm of the metric tensor. Norm of the metric tensor is g alpha beta. G alpha beta is what? Norm of the metric tensor. G square is equal to delta alpha alpha is equal to 4. Okay, in 3 plus 1 dimension. Like, okay. Alright. Next write down is uses, or next write down uses, that is raising and lowering of raising and lowering of tensor indices. Raising and lowering of tensor indices. Okay. Yeah. So raising and lowering of tensor indices are done by contracting with the metric tensor. Okay. Contracting with the metric tensor G alpha beta. For example, see A alpha is equal to G alpha beta A beta. Okay. So this is the contraction. So we got the metric tensor. We use the metric tensor G alpha beta and we contracted A beta to A alpha. Okay. Suppose this is covariant. This is co. Suppose if I write contravariant of A alpha. So A alpha is equal to, okay, G alpha beta, and this will be your A beta. So see, again contraction happened, but this is for contravariant, this is for covariant. Okay. Suppose if I write another kind of matrix or tensor T mu nu, okay, T mu nu is equal to, how will I write this one? See, G, very carefully, G mu nu, G nu beta, okay, G mu beta, and T, sorry, G mu alpha, sorry, G mu alpha, G nu beta, and that will, here, tell me what it will be, because this is mu nu, so mu nu will remain. So we have to cancel alpha beta, so this will be T alpha beta. Alright? Yeah. This is again, this is co-form, covariant. So what will be the contravariant for? Contravariant T mu nu is equal to, again, G mu alpha, G nu beta, and this one will be T alpha beta. Okay, now I think you have got it. Yeah, this is the contraction, raising and lowering of tensor indices. This is called raising and lowering. Okay, yeah, all right. Okay. So the scalar products are expressed. Suppose if I write scalar products, if I write, so it will be A dot B. I can write it as A alpha B alpha. Okay, and let's see, by using the metric tensor we can write G alpha beta, okay, A beta. Why I wrote alpha beta here? Because I need A alpha. A alpha is your contravariant, so I have to keep the alpha here and beta here, and beta will have to be cancelled out, that's why A beta. Okay, and now B, what, B alpha. B alpha remains as it is. I just have to transform the A part. Okay, A alpha. Okay, yeah, all right. So, um, okay, yeah. Next, um, okay, okay. See here, G alpha beta, B beta. What can I write? This one. Sorry, B alpha. Sorry, B alpha. What can I write? This one. This one can be alpha alpha cancel out. B beta, right? So I will write that here. A beta will remain as it is, and this one will be B beta, right? Now write it octave number. This will be B beta, A beta, B beta. Okay, okay, yeah. Mm, this can also, yeah, this one should be enough. All right. Next, suppose I take another example. Suppose S dot T. Okay, S dot T. So A is alpha beta, suppose, and T alpha beta. So let's write for this one. So it will be G mu alpha for double kind of this thing. G mu alpha. Mu have to be, mu has to be cancelled out. So S what? S what? Mu, right? Okay, sorry. G mu nu beta. For this one also we have to write. After that we will apply S. For this one, what? Mu have to be cancelled out. So mu and what mu has to be cancelled out for this, and t alpha beta will remain as it is. Alright, did you get it? Yeah. Mu cancelled out, nu cancelled out, so s alpha beta remains. If you see, s alpha beta remains as it is, t alpha beta will be there. Okay. Yeah. All right. So if we, with this can be 1, so s mu nu and t, we can, okay, no, if we do this with t alpha beta now, see, alpha beta will cancel it. Okay, now what will I do? See, g mu alpha, g mu beta, s mu nu, t alpha beta, correct? So now I will operate this thing on t alpha beta. So alpha beta will be cancelled out. So t mu nu we will get. So it will be s mu nu into t mu nu. Got it? Yeah. Alright. So we transform like s alpha beta, t alpha beta. We equated it to s mu nu, t mu nu. So this kind of transformation can also be in there. Right? So this is right another point. Like for the metric tensor, the trace is equal to the norm. Okay, so g alpha beta into g alpha beta is equal to g alpha alpha. Okay, like beta beta can be cancelled out, which is delta 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 alpha alpha, which is your g square. Okay, yeah. So this is, these are the what uses lowering, raising, all of that. Okay, next write down the Minkowski metric. The Minkowski metric. The Minkowski metric. Okay. Special relativity gives rise to a very special form of the metric tensor. That is your g alpha beta equals to, like, it gives rise to eta alpha beta. Okay. This is referred to as Minkowski metric. Minkowski Minkowski metric, right? And which is actually diagonal, yeah, and with each non-vanishing element normalized to unity. Anything that is non-vanishing or non-zero, that is normalized to unity in magnitude, right? So we can write eta alpha beta is equal to diagonal, okay, 1 minus 1 minus 1 minus 1. This can be written as like this, the one I wrote yesterday, 1 minus 1 minus 1 minus 1, and this is written like this. That means all of these are 0, all of these elements are 0 here. Okay, yeah. Okay, so the magnitude of eta alpha beta or determinant is equal, can be written as delta alpha beta, okay, which is 1. Yeah. Okay. So suppose we can also write x eta 0 0 is equal to 1, eta 0 I is equal to 0 for all I is equal to 1 2 3. Once this thing changes, once this alpha is not equal to beta, this becomes a 0 because it's also like delta kind of thing. And eta ij is equal to minus delta ij. If you can see it here, for ij, for all ij is equal to 1 2 3. Okay, see, these are what, eta 1 1, eta 2 2, eta 3 3. These are minus 1, right? These are minus 1. So yeah, minus delta ij, because delta ij, why are we writing in the generalized form? Okay, because delta 1 1 will be 1, of course, delta 1 2 will be 1. Yeah. Okay. So next write down, next heading, vectors and tensors in Minkowski space. Okay. Vectors and tensors in Minkowski space. So let's now see how the Minkowski metric tensor. Eta Minkowski metric tensor is which one? Eta alpha beta. This is your Minkowski metric tensor. Okay. Let's see how this one helps in identifying or correlating the contra and covariant components of a vector or tensor in relativity. Okay. So let's first write components of a vector. Components of a vector. Okay. Components of a vector. So the components of a covariant vector, suppose A alpha. Okay. I'm writing in shortcut A alpha are related to the components of a contravariant vector, suppose contra. That is your A alpha. Alpha will be upside. So how they are kind of related? How we can relate them? We can relate them via the Minkowski metric tensor. So that is A alpha, A covariant alpha. Okay, A co alpha we can say also is equal to eta alpha beta, which is co, and this is A beta, which is contra. Okay, yeah. So here see beta beta cancel out, so eventually it is A alpha, right? So this can be written also. See here A zero, suppose I write A naught. So eta naught zero beta, okay, eta zero beta A beta. Right, we can write it as eta zero zero A zero, which is eventually A zero, because eta zero zero we have studied is one. Eta one one is minus one. Okay, suppose I write A one. Okay, A one, suppose eta one beta A beta. So this is one. So eta one one A one. So I can write it as what? Eta one one is minus one. So minus one. Okay, exactly like that. A2, A2 is eta 2 beta, A beta, and this one will become eta 2 2, A2, which is minus 8, of course, because eta T2 2 2 is also minus 1. A3 is eta 3 beta, A beta, which is equal to eta 3 3, which is A3. So this is also minus A3. Okay, because we just saw that this is minus 1. That means eta 1 1 is equal to eta 2 2 is equal to eta 3 3 are all minus 1. Okay. So yeah. So in generalized form, I can write AI is equal to eta I beta, A beta is equal to eta I j A j, right? Yeah, you can write like that, where I can like minus delta ij I can also write. Yeah, because I if I is equal to j, of course delta 1 1, that is minus 1. Okay, yeah, delta 1 1 is 1 and this is minus, so minus 1. Okay, yeah. So in the ordinary Euclidean space, the parallel projections like AI, this AI defines the what components of a three vector. So if I write but in like this four-dimensional one, we can write A alpha is equal to what? A naught AI. Okay, and we have done this so many times now. A naught, because A naught, we just proved A naught is equal to A naught. The transformation from core to contra remains the same for the zeroth component. Okay, for the zeroth component, it remains the same. We just here. Okay, but for the first component, first, second, third, it becomes negative. Okay, so it kind of A naught A1 AI, so A naught and minus delta ij. I can write it minus delta ij aj as we did, like A naught minus A1 minus A1 minus A2 minus A3, right? Yeah. So this whole thing can be written as A vector. Okay, I can add minus A vector, correct? Like X vector we used to write. So this is your A vector. Okay. Yeah. These are the components of vector. Right. Next, we can add a components of a second rank tensor. Components of a second rank. Components of a second rank tensor. Let's see. Let's see. So the covariant and contravariant components can be related as what? This is your co T alpha beta can be related as eta mu alpha eta what? Tell me. Mu beta, and this one will be what? Mu need to be cancelled out. Mu. Got it? Yeah. So again, let's write all the components. Write all the components like 0 and all 1 to all of that. Eta 0 0. Okay. Eta 0. Okay. Suppose T 0 0. Suppose let's say T 0 0 is equal to eta 0 mu eta 0 beta, and this one will be T 0 0. Right? T 0 0, which will be, this is actually what? Eta 0 0 square. Okay, and T 0 0, which is eventually T 0 0. Okay, so again the zeroth component remains the same. Now T 0 I is equal to, suppose T 0 1, suppose eta 0 mu eta 1 beta, and this is 0 1, right? 0 1. Okay, so this becomes eta 0 1 square, and this is T 0 1. Okay, so it's kind of, it will become 0 eventually, because here this one is actually delta ij t 0j, right? So delta 0 1 is 0, because this I is not equal to 0, so this thing will become 0. Okay, yeah, only when this is equal to, this are equal, we will have a something like Tij. We can write Tij is equal to eta I mu eta j bit j, sorry, we're doing mistake here. This is alpha, sorry, this is alpha. Okay, eta I alpha eta j beta um, t sorry, sorry, alpha bit, no, my bad, I'm sorry. I was first time I had written correct. This is like alpha beta, like, okay, mu 0 mu 0. Okay, mu 0 mu 1. Yeah, that will be all right. Or 1 mu, the ulta also you can write. Okay, so this one will be I alpha j beta. Sorry again, man. Sorry. Mu j mu t mu is equal to. Okay, don't get confused. Okay, take your time, take it slowly. Do this thing slowly. Okay, then only you will be able to understand. Don't rush it. Delta. See, these things don't need to memorize. Just generalized versions. You'll be able to write them yourself. Okay, don't worry about them. Yes, yeah. So this will be the one. So these are the components of a second rank tensor. Okay. So again, let's see. So here again, eta 0 0 is simply eta 0 0, which is the one. Okay. Eta 0 I is actually your eta. It is 0. Okay. Eta 0. Okay. Eta ij is the real deal. Eta ij is equal to minus delta ij. We've done it so many times now. Okay. Also eta ij can also be minus delta ij. Sorry. Okay. So we can say that eta alpha beta, we can say eta alpha beta and eta alpha beta have the same set of components. Okay, that is diagonal. You can write like this: 1 minus 1 minus 1 minus 1. For higher rank tensors, we can like the relation between contra and covariant could be found in a like similar manner. Okay? We won't go into that high dimension about. Right. Next is your tensor symmetry and antisymmetry. Next is your tensor symmetry and antisymmetry. Tensor symmetry and antisymmetry. Okay. Symmetric and antisymmetric tensors. Symmetry or antisymmetry defined only for contra and covariant tensors for rank less than or equal to 2. Okay. So there are two types. Like it can be symmetry or antisymmetry can be partial, like or can be complete. So these are two types of like symmetry and antisymmetry. Okay. So let's see rank two tensors. Suppose rank two tensors. Okay. There is a symmetric is your what? A is alpha beta is equal to S beta alpha, right? So we can also write this I as alpha beta is equal to S. So this is symmetric. What is antisymmetric? Antisymmetric can be A alpha beta is equal to minus A beta alpha. Okay. Or for contravariant A alpha beta is equal to minus A beta alpha. Yeah. Just write it down. Right. Let's see for rank 3 tensors. So for this one there is partial and complete symmetric. Let's suppose symmetric tensor. So this is there is partial symmetric and there is complete symmetric. Okay. So partial symmetric is what? S alpha beta gamma is equal to S beta alpha gamma. Okay. Or you can go on. Alright. This is kind of called partial symmetric. You understand it when once I say what is the complete symmetry. So what is complete symmetry? Complete symmetry is S alpha beta gamma is equal to S beta gamma alpha is equal to S gamma alpha beta is equal to S all the combinations possible. Okay, all the combinations and everything, all are kind of arrangements. If they are all equal, this is called your complete symmetry. But like partially, like step by step, like this not equal to this, so that's called your partial symmetry. Okay. Even same goes for antisymmetry also partial and complete. Antisymmetry again partial and complete. Again partial, tell me. I hope this is for you to write. I will give you this one. Exactly like this or you have to write. Okay. This is for your homework. Alright. Next given next given symmetrization. Symmetrization anti-symmetrization and anti-symmetrization of tensors. Okay. Symmetrization and anti-symmetrization of the tensors. For rank 2 tensor, for rank 2 tensors. Okay. So suppose let's say um, T alpha beta. So T alpha beta can be symmetrized as T alpha beta plus T alpha beta. Okay, now you'll be like, what is this? What I have written? What I have just written? You'll be like, what is this? Okay, don't worry. So this is T alpha beta is equal to like square bracket. This is called the normal bracket. If I write, so this is equal to T beta alpha is equal to half of. You must have studied in matrix. Okay, beta alpha. Okay, and what is this one? You can guess. It's like the anti-symmetric part. This is very easy. There's nothing else here. It's just a notation, the brackets that will confuse you. Otherwise, there's nothing. A minus of T beta alpha. Okay, so we can say like half of T alpha beta minus. It's just the opposite one. Okay, that's why it's a this kind of sign. So if you add them, you will eventually get this T alpha beta. Okay, so let's add them anyway. Let's add them T alpha beta bracket plus T alpha beta square bracket. So let's add them. This is half T alpha beta plus T beta alpha plus half T alpha beta minus T beta alpha. See here, this term, this one can be cancelled out. Okay, so what remains half T alpha, half T alpha beta, so becomes T alpha. Okay. So this is eventually your this one. Okay, yeah, we proved it. I hope you got it. Okay. So the symmetric part. So this is called, the important thing is now this is the normal algebra. This part is called the symmetric part, like in tensors. Symmetric part, antisymmetric part. This is your antisymmetric. This is your anti-symmetric. Okay, this is a symmetric part. This is your anti-symmetric. So the summation of them, the addition of them will give me normal T alpha beta. Okay. So this thing, this symmetric part is called the and symmetrization of T alpha beta. Okay. So this T alpha beta, this is called symmetrization. We are symmetrizing it. Symmetrization of the original one T alpha beta, and T the square bracket alpha beta will be called what? Simply anti-symmetrization of T alpha. Okay. Both these parts transform like second rank covariant. So we can write down they transform like both of them because these are covariant tensors. Like second rank covariant tensors. Okay. Such a splitting is also possible for the second rank contravariant tensor, that is T alpha beta. You can easily do it. Okay. However, like splitting into a completely symmetrized part, a completely anti-symmetrized part is not possible for a rank greater than 2. Okay. So, yeah. Okay, next is your rank 3. Let's do for rank 3 tensors. Let's do for rank 3. For rank 3 tensors. For rank 3 tensors, we will do the symmetrization and anti-symmetrization. Suppose a covariant tensor, I will take rank 3, that is T alpha beta gamma. This is rank 3. Three kind of indices are there. So T alpha beta gamma, the symmetric part will be what? Let me write 1 by 3 factorial. Okay, remember it. And all the possible combinations we will write gamma plus T what alpha gamma beta. Okay, now plus T beta alpha gamma plus T beta gamma alpha plus T gamma alpha beta plus T gamma beta alpha. Okay, so this is your symmetric part of this symmetrization. Okay, and this is complete symmetric. If you see, this is complete symmetric. This is not partial. This is complete symmetric. Okay, this is now alpha beta gamma. So 1 by 3 factorial T alpha beta gamma plus T beta gamma alpha. Just see this one. T gamma alpha beta. I've written all the proper cycles. Now minus of this one T beta alpha gamma plus of this one T minus, sorry, minus T gamma beta alpha. Okay, watch it carefully. Minus uh, T beta alpha gamma. Okay. Sorry, I wrote this one here for this one. Okay, I hope you got it. And if you add them again, you will get the same thing. So these are actually complete symmetric and complete antisymmetric. This is complete antisymmetric. The other one is completely symmetric. Okay. The thing is here, the linear combination, the addition will not give us the original tensor T alpha beta gamma. Okay, as a bit of here. Okay. So let me write in principle symmetrization, anti-symmetrization of any general, suppose covariant rank of covariant tensor rank greater than 2. Okay, in a d-dimensional space-time, if I write, so it will give me, see, T alpha 1 alpha 2 dot 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 alpha p is equal to 1 by p factorial summation p T alpha p1 p2 alpha p p. Okay, and it's anti-symmetrization alpha 1 alpha 2 beta 1, yeah, same, alpha p give me 1 by p factorial summation p minus 1 to the power p T alpha p1 p2 alpha p. Okay, yeah. Okay, next we will do um, the Levi-Civita tensor. The Levi-Civita, this one is a epsilon, okay, tensor, and the generalized Kronecker delta, the Levi-Civita tensor and the generalized Kronecker delta. Okay. In d dimensions, the maximum rank completely antisymmetric tensor is proportional to Levi-Civita. Okay, right on this point, in d dimensions, capital D dimensions, the maximum ranked completely antisymmetric tensor, completely antisymmetric tensor is proportional to is proportional to the Levi-Civita tensor, the Levi-Civita tensor. Okay, which is defined by what? which is defined by, we can say, T. This is antisymmetric, so square bracket alpha 1, alpha 2, dot dot dot, alpha D. D dimension, no? So alpha D is proportional to Levi beta, which is your epsilon. Kronecker delta is delta, Levi beta is your epsilon. Okay, epsilon 1, epsilon 2, alpha, sorry, alpha 1, alpha 2, dot dot dot, D dimensions alpha D, which is equal to actually minus 1, which is minus 1 for what? Even permutations of alpha 1, alpha 2. For, write down, for alpha 1, alpha 2, dot dot dot, alpha D, uh, and even permutation. Don't worry, you will understand. Even permutation of 0, 1, dot 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 D, and it is equal to 1 for odd permutation. Okay, alpha 1, alpha 2, dot dot, alpha D, an odd permutation of, okay, of 0, 1, dot 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 D, right, and 0 otherwise. Alright. So the so let's write some contractions of Levi beta. Okay, which is very important. Contractions are the most important parts because they are actually used while we solve anything. Okay, so Levi beta, epsilon, mu nu, lambda, sigma. Okay, Levi beta, mu nu, lambda, sigma is actually equal to minus 4 factorial. Okay, very important. Okay. Next, minus 4 means 4 factorial minus. Okay, minus 24, not like 4 factorial. Now, mu, nu, lambda, delta, okay, alpha nu, yeah, lambda delta. There is a slight change of indices here. It was mu here, and now it is alpha. So we have to adjust that, right? So minus 3 factorial. How to adjust it? By delta. Okay, mu alpha. Did you get it? I hope you got it. Yeah, we have done this kind of things enough to just this one. You have to remember. Now alpha, you will understand slowly. Don't worry. Alpha, lambda. Now what will I do? Tell me. Guess. I will change two indices here. Okay. I changed one here. Now I will choose two indices. So it will be alpha, beta, lambda, delta. Now if I do, now what will become? What will it become? Tell me. Minus 2 factorial. Okay. So there is a pattern. There is a pattern. And now what will happen? Mu nu in the upper part and the co part, it will be alpha beta. See, it's not that hard. Okay, it's not that hard. Just have to focus a bit and you will understand. Now what will I do? I will change everything. Okay, I will change everything. Mu, lambda, here, divided by, not everything, sorry, like 3. Okay, sorry. In place of lambda, let's take another one, gamma. Okay, let's take gamma and sigma remains same. Sigma is the only one here. So minus 1 factorial. Okay, delta, three changes, mu, lambda, and this is alpha, beta, gamma. So minus 1 factorial is eventually minus 1. So minus delta, mu, nu, lambda, this is lambda, okay, and alpha, beta, gamma. Okay, yeah. So where we can define this Kronecker deltas. Okay, let's define this Kronecker delta. So if we define it, where we can write where delta mu nu alpha beta is equal to delta mu alpha delta mu beta delta mu. Now mu, first column is your mu. Okay, second column is your nu. Simple. Alpha nu beta. First row is alpha, second row is beta. Simple. Okay. If I write for the 3 by 3 matrix, suppose mu, nu, delta, sorry, lambda, alpha, beta, gamma. Okay, delta mu, alpha. Again, first row is completely alpha, so I will just change the indices in upper part. Mu alpha, lambda alpha. Got it? Very simple. Second row will be simply beta, so mu beta, nu beta, lambda beta. Third row will be completely gamma, so mu gamma, nu gamma, and lambda gamma. Okay, very good. That's what it is. Okay, that's the way to understand it. Okay, very simple. You can really do it. So these are the generalized chronicle delta tensors. You can say generalized. You can say generalized chronicle delta tensors. Yeah. All right. All right. So that will be it for this class. Next class we will study more about this. Like next class we will study tensor duality, which is again very important. Tensor, and we'll go into tensor calculus, okay, which is the most important part of it. All the applications are there, and using tensor calculus only, we will study relativistic electrodynamics. Okay, in the coming sessions. Okay, thank you very much. Thank you.